Hi again, everybody. Welcome to our third video on partial fractions. In the first video, we handled what is sometimes called the distinct linear factor case. So distinct linear factor case, and that's when you had something, it doesn't really matter what's in the numerator, so I'll just write a 1. We could have more things here. But I have a linear factor, say an x plus 3, and another linear factor, x minus 1. And the word distinct means different here. Okay, these are not the same thing. If I had x plus 3, then I'd be in the second case, which we covered in the second video, which is having repeated linear factors. So when you have a repeated linear factor, then it could be something like x minus 1 squared. And, well, it's actually not so convenient to just write a 1 here. Maybe we had a 1, but then also a 3x plus 1. Okay, so this would be a case where you have a repeated linear factor because the x minus 1 shows up more than once. In this video, we're going to squish these two together. We're going to have distinct linear factors and we're going to have repeated linear factors. For example, this example. So here, well, you have some numerator, but in the denominator, you'll notice the x minus 2 is occurring 2 times. X plus 1 occurs 1 time. X plus 1 is not the same as x minus 2, so there's a distinctness. But x minus 2 and x minus 2, those are the same. There's a repetition. So we have both a repeated linear factor, the x minus 2, and we have distinct linear factors, x minus 2 and x plus 1. Question is, how do we do the decomposition? And the answer is you do it in the most naive way possible, and it works. How do we know it works? There's a theorem for that too. So the theorem is going to tell us that I can decompose 7x squared minus 21x plus 8 over x minus 2 squared x plus 1 into 3 fractions. The first one, well, we just follow the repetition pattern. I first write x minus 2 to the first, then I write x minus 2 squared. And then for this other linear factor, well, I just handle it like normal, plus x plus 1. And again, there will be 3 constant terms, a, b, and c. And now we proceed exactly as before. There's nothing else to do. I'm not even going to work through this example. I'll tell you in the end that the a and the b and the c are going to equal. Pause here if you don't want to know the answer, but you should work through this and find these for yourself. The a, the b, and the c are going to equal 3, -2, and 4. Give it a try. When you come back, we're going to talk about one little technicality that we haven't really covered with any of these things yet. Okay, welcome back. So I promised you I was going to tell you about a little technicality, and let me get to it. Let's look at another example. We'll add a dx here to be at least a little more precise. Say I wanted to find an antiderivative for x cubed minus 1 over, well, x plus 3x minus 1, which you may recall from our first video on partial fractions. If we follow the normal plan, without thinking, we would say x cubed minus 1 over x plus 3 times x minus 1 equals some constant over x plus 3 and some constant over x minus 1. Okay, we'll give names a and b. Now we try to solve it. How do we do it? We multiply through by x plus 3 times x minus 1, and we get x cubed minus 1 equals a times x minus 1, because the x plus 3's cancel, and b times x plus 3, because the x minus 1's cancel. Fine. I go to distribute this, and I notice I get a plus b x's, and then I have negative a plus 3b. So negative a plus 3b. Next step, I try to equate the coefficients. So let's start with the x cubed. On this side, I have 1x cubed. On this side, I have, that's a problem. There are no x cubes. And you might say, oh, well, that's okay. You set something equal to 0. Not good. No. Let's put this in here. If I insert here a plus 0x cubed, then 0x cubed has to be the same as 1x cubed, and 1 does not equal 0. We've got a problem. And the problem is, well, the theorem I've been talking about over the last couple of videos, which says that these decompositions exist, it has an assumption. And the assumption is that the degree, the highest power of x that you start with in the numerator, is smaller than the degree in the denominator. You don't want, so here the degree would be x squared, because if I distributed this, I'd get x squareds out. You don't want this here having a higher degree, or even equal degree, to the one in the denominator. Well, what do you do if it is? The answer is, you have to go back to your algebra skills. You do some polynomial division. If I take this polynomial, divide it by the denominator polynomial, I'm going to get some polynomial plus a remainder. Now that polynomial you get, you're going to be able to integrate that no problem. The remainder you get will have the desired property. Okay, let's wipe this away and give an example. All right, so let's do the following example. I want to find an antiderivative of x squared plus x plus 1 over x minus 1 times x plus 1. So we note immediately the degree of the numerator equals the degree of the denominator. I have an x squared here, and if I distributed, the highest term would also be x squared. So I don't immediately jump to partial fractions. Instead, I do polynomial division. So I'm going to take x squared plus x plus 1, and I'm going to divide it by this product. Well, you should recognize this from the difference of squares formula as being x squared minus 1. If you don't, well, just distribute it out. You'll get x squared minus 1, hopefully. All right, when we do polynomial division, I ask how many times does x squared go into x squared? Okay, that's 1 time. 1 times x squared minus 1 is x squared minus 1. I subtract. X squared minus x squared is 0 x squareds. X minus nothing is x. And 1 minus negative 1 is 2. Okay, now x squared minus 1 will not go into x plus 2, so I know I'm done, and this must be my remainder. So I must get plus x plus 2 over x squared minus 1, which means I can rewrite this antiderivative. So antiderivative of x squared plus x plus 1 over x minus 1 x plus 1 dx. Oh, I guess we should have a dx over here too. Equals antiderivative of 1 plus, and there is our remainder, x plus 2 over x squared minus 1. Okay, now the 1, that's going to be really easy. And this bit, well, if we just put the x squared minus 1 back into x minus 1 times x plus 1 form, we can use partial fractions now. So this is just something you need to get into the habit of looking at really quickly when you decide to use partial fractions. Is the numerator, does it have smaller degree than the denominator? If not, maybe you do some partial fractions work before you go about doing it. Otherwise, no bueno, no bueno.